Hi everyone. This week we're going to talk about the trig graphs, and we're going to start with sine and cosine, and then afterwards we'll talk about the other four. And we're really going to mainly focus on sine and cosine because those really are the two most important ones. Those are the ones you guys are going to use most often. You'll see them in AP Calc a little bit. You'll probably see them in your physics class. They're very common graphs, so we're going to focus on those two. So the first thing we want to do is realize that sine and cosine are both what we call oscillating functions. And the word oscillate means to go back and forth repeatedly, basically forever. So a good real life example of oscillation would be like the hand on a grandfather clock that swings back and ticks every second away. That's an oscillating real life situation. Things like that, a pendulum. But basically sine and cosine are both oscillating. What oscillating actually means is that you are following a cycle and you're repeating it over a certain period of time, or in this case a certain x value period. Now we just finished learning the unit circle, and we know that for trig functions they repeat every time you go around, and there's your oscillation, there's your period right there. So basically every 2 pi, whatever you're working with, sine, cosine, tangent, any of the six, once you start at 0 and you go around, once you hit 2 pi, you're just starting over and doing the exact same thing again. And that's why you have oscillating functions. So basically, if we take a quick look at sine and cosine, I'm going to kind of stretch my graph out. Let's say this is 2 pi right here on the x-axis. What sine does is it starts at 0, it goes up, down, and ends at 0. Now after that, it repeats. So you basically, that little wave shape, a lot of times we call it a sine wave. You get that wave shape that just repeats forever, and it goes in both directions. Up and down, up and down, up and down forever. Now a cosine graph has the exact same shape, but instead of starting at 0, it starts at +1. And that, again, that's straight from the unit circle. If you go to 0 degrees or 0 radians on the unit circle, sine of 0 is 0, and cosine of 0 is 1. But basically it just follows that curve pattern. It does the same thing, but kind of right behind it like this. So you can actually think of sine and cosine as the exact same graph, but one of them has been scooted over a tiny bit. If you take either sine or cosine and do what we call a horizontal shift, just move it over a certain amount, then it will basically turn into the other graph. So those are your two graphs. They look very similar. The only difference is where they start at 0. For sine, it starts at the origin at 0, and for cosine, it starts up 1 point. But you get that repeating, oscillating wave shape, up and down, up and down, up and down forever. Okay, so here's an important note, not just about the graphs, but about sine and cosine in general. Whenever you're doing sine or cosine, your answer, the biggest it can be is +1, and the smallest it can be is -1. You can never have a sine or cosine value that's bigger than 1 or less than -1. And the reason for that actually comes from SOHCAHTOA. If you think about it, sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Well, we know from SOHCAHTOA that the hypotenuse is the biggest side of a triangle, which means out of opposite, adjacent, and hypotenuse, h is the biggest number. So if you have a fraction with a bigger number on bottom, then your fraction can't be bigger than 1. So really both of these ratios here, opposite over hypotenuse, sine, and adjacent over hypotenuse, cosine, you're always getting a number that cannot be bigger than 1. It's going to be some sort of fraction or decimal that's either equal to 1, that's the biggest it can get, or less. All right, now what that means about our graph is, remember how our graphs are going up and down, up and down, up and down? The highest they ever reach, the peaks, are at +1, and the lowest they ever reach, the valleys you could call them, are at -1. So this graph, both graphs actually, are just bouncing back and forth, up to 1, down to -1, up to 1, down to -1, forever. Now that's called the amplitude. Amplitude is basically like the height of the function, although it's not technically the height of the whole thing. It's basically the distance both up and down. So if you're going up to 1 and down to -1, if you really thought about it, the height of that graph would actually be 2, because you're going 1 in each direction. And that's not what we mean by amplitude. So it's not technically the height. It's like the height measured from the x-axis. How high up do you go down? How far down? Now, if you take one of your functions, sine or cosine, and you multiply it by a number or another function, and the other function one is going to get interesting. But if you take your sine or cosine graph and multiply it by something else, that changes the amplitude. So for our first example, let's sketch y equals 3 cosine x. And I'm going to start, even though we just drew it, let me just start. Let's say this graph right here is going to just be cosine x, first of all. And we know that cosine x goes up to 1 and down to -1. And it starts at +1. So basically you can draw in these lines if you want. You can say, this is -1, that's the lowest I'm going to go. This is +1, that's the highest I'm going to go. I have my starting point. From that starting point, I'm just going to draw that oscillating shape that goes from red line to red line in both directions. So if I wanted to draw 3 cosine x, which is what I asked you guys to do, what you would do is instead of going up to 1, you would go up here to 3 and down here to -3. So for my, I left space to do the question separately. I think I'd rather just do it right on top of this one. Let's just do the graph right here. So instead of 1, my graph is going to go all the way up here to 3. And instead of -1, my graph is going to go way down here to -3. Now that means the starting point also moves. So for my graph, I'll switch colors here, we'll do it in blue. My graph is going to start right here at 3, and then it's going to follow that same up-down pattern, but it's going to go all the way up and down to the purple lines instead of the red ones. So you get this taller, stretched out cosine graph to look something like that. So basically, the graph of whatever you're doing, sine or cosine, if you take the number in front of it, +3 is the top of your graph, and the negative version of that is the bottom. Okay, so now let's look at what happens when you take one of your trig functions and instead of putting a number in front of it, or instead of multiplying by a number, you multiply by another function. So remember, the last one we looked at had a cosine x, and we multiplied it by 3, and that meant the graph goes up to 3 and down to -3. Well, I'm going to do kind of the same thing here. I'm going to say positive e to the x is going to be the top of my graph, and negative e to the x is going to be the bottom of my graph. And I'll show you what that looks like. It's actually a very interesting graph. So let's say we'll graph it right here. Now I'm going to draw a quick sketch of e to the x. Doesn't have to be perfect, just a sketch. We did this a few chapters ago. E to the x is an exponential graph that starts near 0 and turns up like this. And negative e to the x would be the reflection of that. It would be the same thing but under the asymptote. It would start near 0, turn down, and look something like that. Now what I want to do is I want to draw my sine graph, but between those two, not perfectly horizontal lines, but between those two curves. So I would say sine starts at 0, and then it's going to go up to one line and down to the other and up, and all of a sudden it's off our graph already. And on the other side, it's actually shrinking. It's flattening into the asymptote. It's down and then back up and then down, and all of a sudden it looks almost like a straight line there. So that's something interesting for you guys. I think you did sine and cosine graphs last year, and I think you did amplitude last year. But here's something you may not have seen last year. What we call amplitude, what's usually just a number, can be another function, and you get very interesting looking graphs there. So what I want to do here is pause. I'm going to go to Desmos, and I want to show you these same two graphs on Desmos just to give you another look at them, because I think it'll help you see what's really happening here. All right, so here we are in Desmos. I pre-typed in all the equations that we're going to need, and I'll just kind of light them up one at a time. So here is 3 cosine x. I'll zoom out a little bit, but you can see it's that oscillating function that just repeats up, down, up, down, up, down. But it's going up instead of, whereas just cosine x by itself goes up to 1 and down to -1, you can see this one has kind of a top at y equals 3. That's the blue line right there. And a bottom at y equals -3. That's the green line. So by imagining that horizontal line at +3, and a horizontal line at -3, what we're doing is we're drawing a cosine graph that just kind of squeezes in between those two lines. Then for the next one, I said, let's look at e to the x sine x. So before I put the graph in, I'm going to go backwards. I'm going to do the boundaries first. So I said it's not even really called amplitude, but our bounding function is e to the x. So if I graph positive e to the x, it looks like this black one here. And if I graph negative e to the x, it looks like that red one there. So what we want is a sine graph, but it's squeezed in between those lines. So to the right, it's going to get very, very, very big. But to the left, it's actually going to squeeze down until it almost looks like just a horizontal line. And this is what that graph would look like in purple there. So for this one, I'll zoom it back in a little. You can see how it is that sine graph, and to the left, it's getting squeezed between those two lines. It's basically disappearing. You can't even see it anymore. But to the right, it's getting bigger and bigger and bigger, and if I zoom way out, all it looks like is a bunch of horizontal lines, because e to the x gets so big, we're not going to see the top or bottom of that graph. Okay, we're back. We talked about amplitude. We took a look on Desmos. Now what we want to talk about next is the period. We said earlier in the notes that the period is basically how long it takes for one cycle before it starts repeating. And we decided that for our trig graphs, for sine and cosine, it's 2 pi, because that's one trip around the unit circle. So whatever your values are for sine or cosine, if you figure out the values from 0 to 2 pi, it then just starts over. And you get the same values again, and again, and again, and it keeps repeating. So basically, if you figure out what that one cycle looks like of each graph from 0 to 2 pi, that same piece just repeats over and over. Now, just like amplitude, we can change that number too, though. And the way we change that number, change the period, is when we have a number not in front of the trig function, like last time we did 3 sine x or 3 cosine x. Well, all of a sudden, the number is going to be inside the trig function on the variable. So it might be cosine of 3x. That's what changes the period. So for our example, we're going to go back to Desmos. We're going to graph these 4 things one at a time and compare them. We're going to do, first of all, just a sine x as our baseline graph. And then we're going to do sine of 2x and see what happens. Sine of 5x. And then I threw a fraction in there. We'll do sine of 1/2 x last and see what that looks like. All right, so here we are back in Desmos. I typed in the 4 equations that we wanted to graph, and I'm going to bring them up one at a time again like I did last time. So first of all, let's just start with sine x. And I'm going to leave this one on as we do the others so you have a comparison. So this is just our ordinary sine x graph. One cycle goes from 0 to 2 pi. And remember, 2 pi would be 2 times 3.14, about 6.28. And if you look at the x-axis, it's ending just past the 6. So that's 0 to 2 pi. So what I'm going to do, I'm going to bring up sine of 2x next. And we said it's going to change the length of one cycle. Now, what we might think is, okay, well, I'm multiplying it by 2, it's going to make it twice as big, and you're going to end up with a longer graph. But it actually does the exact opposite. You end up with a shorter graph. a quicker turning sine wave. So basically what you're really saying when you do sine of 2x, what you're actually saying is I'm going to fit 2 full cycles within my one normal period. I'm fitting 2 cycles between 0 and 2 pi. And if we get rid of that one and do sine of 5x, you see one that turns much faster even, the green one. And again, that's because what you're really saying is I'm taking 5 complete cycles and fitting them into my normal period from 0 to 2 pi. So you get a very fast turning, up, down, up, down, up, down, up, down. It repeats itself 5 times just between 0 and 2 pi. Now the last one, sine of 1/2 x, does what we might have expected on 2x. It actually stretches it and makes it longer. So what you're seeing this pattern where the bigger the number gets, the shorter the period gets, the shorter the sine wave gets. It starts turning very, very quickly. Whereas if you have a smaller number, a fraction, it gets longer. So let's go to back to the notes and talk about exactly how to determine the period. All right, so basically from Desmos, what we figured out is that multiplying by x changes the period, but it's kind of backwards from what you might expect. Like for example, if this is one period of sine x, let's say that's 2 pi right there, and this is sine x. If I did sine of 2x, without knowing the rule, your guess might be, okay, we're multiplying by 2. It's going to make it twice as long. It's going to go like this. But that would be wrong. That actually ended up being sine of 1/2 x. Sine of 2x made it shorter. Sine of 2x made the whole thing fit in half the graph. So what we're really learning is when you're looking at the variable, if you're multiplying by a number, the bigger the number, the more squished it gets, the more quickly it twists and turns up and down, up and down, up and down very fast. Whereas if you get a number less than 1, like 1/2 or 1/5 or 1/10 or 1/100th, it basically stretches it really, really wide and you get these big, slow curves. Now the rule to find the exact period is you divide. Basically you take your original period, which is 2 pi, and just divide by the number in front of x. So basically if you have one of these two things, we'll call it y equals sine of bx, I'll use b for the number, that's what books do, or y equals cosine of bx, then all you have to do is take 2 pi, divide by b, and that gives the new period. And that's why a fraction makes it bigger, because dividing by a fraction actually makes numbers bigger. Like if I did 2 pi and I divided it by 1/2, dividing by 1/2 is actually multiplying by a reciprocal, it's multiplying by 2. So if I take 2 pi and divide it by 1/2, it's actually 2 pi times 2 and I get 4 pi. That's why the yellow graph there is bigger or stretched out farther than the regular white one. But that's basically what we're focusing on today, is what a sine and cosine graph is and how to affect its amplitude, height, and its period, which is basically length.